Okay, so changing topics a little bit, acoustics. So this is quite a novel enhancement here. We know that we can take data at a point in space and capture temporal data and then do an FFT on it. But what about the opposite? Choosing a frequency and looking how that changes over time as your system moves, or as your system changes. So that's what you can do now. Under this zone specific averaging, we've been able to do mean and standard deviation before. Now you can do min and max, but you can also do this one, which is a Fourier component. And so what it allows you to do is store data over a run and then build up a picture of what a particular wave frequency or wavelength, whichever way you want to think about, is doing. So here's an example of a couple of monopoles interacting. And this is what you're seeing instantaneously if you run this simulation. And this is what you'll get if you look at the different frequencies, because these are pulsing at different frequencies. So this is showing you the pattern belonging to the central one. This is showing you the wave pattern belonging to the offset one here. And you're now capturing where those frequencies are, so in space. We've got an acoustic sponge layer. So this is very much like a artificial beach that you have when you're doing a volume of fluid with waves. So when acoustic waves reach a boundary, you can damp them out. So what you do is you blend the density over this region between its incoming value and some reference value. So you're typically going to be using this at inlet and outlet boundaries to damp out reflected waves in a very efficient way. And then finally, on the acoustics front, we introduced a while ago with the purchase of VX Experience, the ability to play sound files. So you could record sound data and play it back and hear what the sound data would like. We know we can transform data from its point of generation to a far-field microphone using various approaches in Fluent, like the Fox-Williams equation. Ansys have now been working with this code VX Experience, which has been rebadged or renamed as Ansys Sound. And so it can still obviously do those playback of files. But what it can also do is taking data from different sources and sending it off to different receivers, etc. So it can do that propagation based on generated files to different locations and that. So that's something to have a look at if you're doing sound stuff and you want to understand what's going on with generated sound from different sources or at different receivers. Okay, so I've now got just a group of various things that I want to just go through and mention, so you can see some minor things that might be relevant to you. So we all know about when we use the coupled solver, the concept of having a pseudo time step. It's been part of a coupled solver technology forever since it was done. You can now start using this technology with the pressure-based solvers here when you've got something like simple active. So when you're using one of the segregated solvers, and you can think of it as having like a local relaxation factor in every cell if you use it based on CFL numbers. So just like you can use this courant based determination of the time step when you're using a coupled solver, you can start to do that now here. And it's giving you some really good convergence behaviors here. So worth a try. When you make mesh interfaces, you can now adjust the tolerance and you can have a bit more flexibility when you generate them. So we've just some improvements there. Unified remeshing. So this is an exercise that's going on at the moment to improve remeshing. If you go back to an older release of the code, you'll find that when you switch remeshing on, you seem to have to put in an enormous amount of information to get it to work. What they've been doing is putting the best practices in as automatic and giving you very few choices needed when you set up it basically, with a few advanced ones. And keep in mind at the moment this does not include polyhedral cells, but if you're not using polyhedral cells, then there's some really good technology in here now for improved remeshing with your prism layers on surfaces, and also with size field improvements. So imagine you're doing a simulation of a ball flying through the air in a moving mesh. Then you would probably start off with quite a coarse background mesh and a nice refinement around the ball. If you don't do anything special and start remeshing, that refinement stays where it is in physical space, and the ball just goes out into coarse mesh, and when it's remeshed, it stays coarse. What this size field improvement does is allow the code to capture the size fields around an object and move them with the object, so that the good quality mesh around the object just moves with it. So that is a really good improvement there. Obviously, this needs to move to polyhedral and it's ongoing work, but there's some really significant improvements if you're using TET and prism meshes. Just by way of reminding you that there's intrinsic FSI capability within Fluent. So there's a mechanical solver for linear elastic materials, and you can do things like bimetallic strip behavior, one-way and two-way FSI. There's been some improvements in that. There's a couple of UDFs been added to do things. You can also use expressions, so you would need to have a really complicated movement if you wanted to use a UDF, but they're now available. There's been work done on gap modeling. So when the gap gets really small, there's one way of dealing with it is to close it up completely. Another way is to use what's called a fictitious viscosity method, where your viscosity goes up in that region and it essentially blocks the flow off. So you've got a small gap there because you can't mesh. You need it for the mesh. So what you can do now is have it build a high viscosity region that essentially blocks it off. And it's got a whole load of tools associated with it now, where you can actually choose the region, you can extend it to give it more or less region over which it blocks. And that, so for anybody dealing with small gaps that they might want to close off or restrict the flow through, there's some good improvements. This is just going back to the very beginning of where we started, if you like, today almost. in this new orthogonal quality methodology. So what you can do is there's this new option under Poor Mesh Numerics of orthogonality enhancing cell centroids. Hit it yes and set a quality, and that doesn't use the orthogonal quality, it uses this new orthogonal quality here and improves things. So you can see here is a case that's going nowhere and a case where once you've done this, it's all improved. So again, this is just tweaks where you move the centroid around in the mesh cell to give that cell a better performance when it's discretized. If you've got 2.5D meshes, so if you like a surface mesh here which is extruded depth-wise, then there's some improvements to the parallel behavior partitioning here that's going to give you improvements. And you can also improve it by having this Laplace partitioning option, which can give you improved behavior, and you can have that switched on under preferences. If you've got multiple reference pressures, then so you've got isolated flow domains, then there's some big improvements to memory and time.